Hey everyone, thanks for being here. I'm presenting on my dissertation proposal today, but first I'm really going to introduce myself and like what I do and what my research is, because like a lot of people don't really know what I do other than like I'm the VR guy. So, but really, I think it's important to talk about me more of like where I come from and how I got here is more important of like kind of knowing who I am. So I started my career with Adam Jones in computer science. I was in CS lab, got a CS undergrad degree. But Adam was really into cognitive science. And after I left there, he recommended me to come here and work with Sarah and Janine, who are psychologists. But, right, they really have strong ties to computer science. And so I've been in this really unique position to be guided by a set of people from both ends of the spectrum of my narrow slice of work that I do. That being virtual reality and describing its strengths and weaknesses. And how I like to think of virtual reality is it's a means to replicate reality in one way or another. This reality can be that of job onboarding. It can be medical operations, like getting familiar with life-saving techniques, or even like learning to operate one of the most complicated machines on the earth, right? So what has all this in common is that each one has the assumption that VR is a suitable enough replacement for reality for this to make sense. Whether or not it's a real good substitution can get you in a lot of arguments. However, there's one quote that I think really encompasses how I feel about this topic, and that is, mistaken perceptions lead to inappropriate actions. That is a quote from J.J. Gibson. And so any inaccuracy presenting in the world in VR would logically lead us to not interact with the virtual world as we would the real world. There's a disconnect there. Therefore, matching perception, particularly visual perception, is super important in VR. This has always been the case. It's nothing super new. We've been doing it all the time. VR perception has always been a satisfying problem, just constantly getting better, sacrificing some things, and saying, this is good enough. Well, I've been really deliberate about the VR headsets I've shown you so far. I've showed you about 9, and they've all been completely unique. And they all fit within this span here. Does anyone want to take a guess on how many VR headsets came out between 2006 and this one got released last month? 40. 52? Yeah.
87.
Actually 150. And so with all of those, these are all multi-$100 headsets. These aren't just like what you find in the Walgreens aisle while you're checking out. It is like everyone's really fighting to be, this is the best VR headset. It beats everything before it. And through all of that, do you really think like we really nailed perception? No, not at all. There's so many issues that are still in VR headsets, but one of them in particular I like to talk about, and it's never been compensated for in any of these headsets, not even a little bit, and that's pupil swim. Now this is a weird topic, just a weird word actually, more than anything. And this occurs when your eye moves or rotates around the lens. So the lens is designed to like project an image properly in this volume. This volume is called an eye box. And when you leave that eye box, well, things get kind of wonky. And the ideal thing is you never leave that eye box, but that doesn't work, right? We always shift our gaze around and move our eyes. So, like, what does it really do? It's really hard to describe. So I'm actually going to start with a little demo. I'm going to do one for myself up here, and then I'm going to pass around some things for you to play with as I talk. So, I actually massacred one of my prescription lenses. So if you have glasses, this is like you can test it on your own, actually. But and I have a laser pointed here. You can see this shows up, it's backwards, shows up roughly okay on this wall right here. I just need to make sure it's stable. So, right about here, so we see the smiley face. I'm not going to move the laser, but I'm going to move the lens around. And you can see that it shifts quite a bit left and right. It's like a quite significant degree-wise. And that's pupil swim, really. And so, but it's really more important for you to experience it yourself. So, in here I have 3 sets of lenses that I've also gotten from a VR headset. So, this one right here, you can just pass it up and down, and I'll show you what you can do with it to really figure out what's going on. So if you hold it just like on the paper, you'll actually get to look at something like this. So over on the left here, we have if your eye was perfectly in line. And let's say you rotated it or just like kind of, you can move it around even, and you can see all the dots not move linearly. They're all going to be kind of warpy around. I took this picture, these 2 from my phone. This one over here, I took it from a slight angle, and you can see the angle up at the top, and you can see how much those lines bend. And this is from one, that's right there. This is from the Oculus Quest, or Meta Quest 2. And this is a Fresnel lens, so it's a little bit more or less prone to changing, while the other ones are more like prescription lenses. They're called aspheric. That's going to come back later, don't worry. No test required. So, as you guys get to experience it, I'm going to talk about it in more of a graphical format. So, let's say we have a tree here, and we have our user looking straight ahead. They see this tree in their periphery, and they want to look at it. So, they rotate some angle to look at the tree. And when they look over, they expect this tree to be in their perception, but actually, they come out short. And that's because they're looking through the side of the lens, and pupil swim occurs. In actuality, they need to rotate even further for the light to bend and to catch that tree. So, really, whenever you look to the side, you're going to have to look even more due to pupil swim. And the real big question is, what's the difference? What's the difference in this angle? How much does that matter? And I'm going to refer to this as delta theta for the rest of this talk. And that's my big question, is figuring out what the heck is delta theta. But before we talk about how we measure that, I want to talk about how this happens. There are 2 major ways. The first one is eye rotation, we talked about just now a little bit. The other one is misalignment. Misalignment occurs when your pupil is not aligned with the lens. It's just positionally out of place, not anything angly, just positional. And the main culprit of this is IPD, or more like IPD mismatch. IPD is interpupillary distance, also known as the distance between the centers of your pupil. To further explain this, why this is the primary suspect of pupil swim, at least in positional case, I'm going to take an example, that being Sarah and Janine here. So, Sarah and Janine have an IPD of 64 and 56 respectively. And I'm going to mark them here by these, blue here, green there, stars. And you can put them on the distribution for women, and men are at the bottom here. And let's take some high-end HMDs and see how they fit. So we're going to take the Vario, this is its span, the MetaQuest Pro, and the HTC Vive Pro. And so you can already kind of see, in this red right here, that's a third of the population that won't be fit in all these headsets. Now, you might look at like third population, like I guess that's passing, right? Like, I'll take that. But remember, these are not your typical VR displays. These are some of the highest end VR displays. This is meant for research, the best we can get. Most people's first experience in VR is actually with something like this. So, I'm gonna take this out of this packaging. And for the most part, these don't have, you can't change the lenses on these. They don't go anywhere. And where they actually are, take that and pass it around. What they're at is at 65 millimeters. Not the average of everything, but the average for the average white male. Thankfully, I'm one of those, and I have a yeah, exactly, right? I have a perfectly split IPD as well. So all these work for me. This, I can perfectly fuse these. I don't get a headache looking at it. Anything. I doubt anyone in here really can look at this and not get a headache from these. Yeah, exactly, right? And I don't get that. It's perfect for me, right? So you can go ahead and pass this around and decide if you think this product was particularly made for you. So now we discuss the two major causes. So let's talk about how could these affect perception. So generally we have two different types of depth cues. We have primary cues and secondary cues. Primary cues are gathered from physiological signals, while secondary cues are gleaned from the environment themselves. Let's talk about secondary cues first, because they're a lot simpler to talk about. One example is linear perspective, or relative size, or motion parallax, occlusion, shadows, all this kind of stuff. It really makes sense to put this in images, but when we talk about primary cues, it's a lot more complicated to explain on a slide. One of these being convergence. The closer objects sit to you, the more your eyes turn inward, and you get that signal and you interpret that as depth. The other one is binocular disparity. You get this from these old-fashioned 3D glasses. So one image shifted to the left, one image shifted to the right, and that gives you a sense of depth from that. However, these cues, or these primary cues, are important because they're the ones that are affected the most by pupil swim. And when these cues conflict with each other, we typically weight one more than the other, whichever one we feel is more reliable, usually our internal cues. But for example, let's take linear perspective. We're in a very geometric room right here. How we build buildings, our environments, they're very standard, and we rely on that. If we compare it to relative size, however, we're all in different shapes and sizes. This can be kind of shifted around and violated a little bit. And that really manifests as something like an Ames room. And so you can see, another facet to consider is our depth cues are more effective in different parts of space. So in personal space, our primary depth cues are better. In our action space, about 2 meters to 30 meters, in that kind of ballpark, that is like secondary cue territory, right? This gives us a thought that pupil swim might be more effective or more detrimental, I suppose, in personal space rather than action space. So you can imagine how dangerous these misperceptions can be in something like medical operations or ill-effective learning. All this is an issue. So that takes us to my aims and experiments. I have 3 particular goals. One is I would like to measure this in multiple HMDs, head-mounted displays. Number 2, I want to see how this is presented in humans through an eye tracking task. And third, I want to see if pupil swim actually affects our actions in the environment. Does it affect depth perception? So does it mean anything that it's wrong? And this is just a reminder, I'm looking for this special delta theta this whole time. This is our golden ticket. So first, we're going to measure pupil swim. To do this, I'm going to map some lenses and HMDs using image processing and some computer vision. And we can use our camera here as our surrogate eye. Oh, went a little too much. However, we already said there's tons of headsets out there. So which ones do I pick? Well, the answer is as many as I get my hands on. Since I'm not using subjects for this particular section, I want them all, right? And what's really awesome is that we have this huge collection thanks to the University of Utah as well as my collaborator over at Mississippi State, Adam. We, along with some personal HMVs as well, this will be the largest collection of headsets to ever be studied in our community at one time. While all those headsets, there's a lot of them, typically they can be set up into 3 categories. And these are aspheric, Fresnel, and pancake. This is a little like whatever, right? We're going to talk about them as aspheric, meaning like prescription glasses. That's the smooth one that you saw passing around. The Fresnel one is like the shark fin, little circular ones. It's more of like a lighthouse lens. And then the pancake, I don't have a good example of it. It's hard to see, but it's usually in cameras or telescopes, actually. So measuring looks something like this. I get a camera, put it into a headset, and then we measure, or we take little pictures of horizontal lines and vertical lines. And then we move the camera a little bit, do it again, and you get 2 surfaces, one being, one with the camera in one place, and the other surface with the camera in the other place, and then contrast those surfaces. And then we can see how much things move. But in reality, it's a little messy. This is what it looks like, actually, when I went to Mississippi State last summer, or maybe 2 summers ago. We did this, and this is my headset strapped to a CNC machine, and I took a GoPro and put it into the drill bit, and strapped down the headset with a belt. And you can see, you get some pretty lines, also some really ugly ones. So there's a big variance between headsets and how much they can handle if you will swim. And that's why, what's up?
How are you accounting for the lens of the GoPro?
Oh, okay. Glad you asked. So, what we're not actually comparing 2 surfaces to each other particularly. So we take the lens of the GoPro and we measure it on a baseline. And we get, by that I'm doing it in a monitor that's completely flat, and I have it cover the whole field of view. And then we get the surface of the camera in camera space. And then we convert these surfaces to camera space. So now we're comparing apples to apples.
Yeah.
So it's because all the terms cancel out at the very end, and that's how we're able to do that.
Because GoPros, the only reason I asked is the GoPros have like a very extreme,
they have
wide
a
angle
fisheye lens, yeah. And so that's why we're able to do it, because normally cameras can't get that close and capture the entirety of the headset. But good question. I'm glad you asked it. Here's some pilot data that we collected while I was there in Adam's garage. And for reference, not to care too much about it, really, oh wow, that one's blown out. Anywhere that's less saturated, anywhere there's more color, that means there's more distortion. So, and where there's less saturation, less distortion. And what that really means, that is our delta theta everywhere, all of that. So we found it, right? And that's really good. So now I just have to do that with the other 30 whatever headsets I want to do. So that's great. Moving on to our next one is, does it do anything in eye tracking? Well, it's kind of daunting to study all those headsets in one participant pool. You can't really do that. So we're going to take 3 champions, one from each category, the Vario, Vive, and MetaQuest Pro. They all have different lens configurations, and they all have pretty good eye tracking. Good for VR, at least. So quickly, I'm going to describe my experiment. We present an object out in front of them. we ask them to look at it. But since we know they're turning their eye during convergence, that tree is actually going to appear over here, and they're actually going to look further over. Eye tracker is going to capture this orange line, and we already know where we put that because that's where we put our stimulus. And we take the difference between that, and that's our delta theta. We found it again. And this is some data that I took. This is from one headset only. And as you look closer, you expect convergence to increase. And so as the target gets closer, you expect pupil sum to increase. Which we see that, actually. This curve right here denotes that. And it gets as bad as to like 15 degrees at 10 centimeters. And 15 degrees is quite a bit. It's probably like that much if you hold your arm out. But we don't know what that does for other headsets. Only know this for one. So that in line the rest of my experiment. So our aim 3 is figuring out, does this mean anything? And does it mean anything in personal space, or does it mean anything in action space, or none of them at all? So let's start with action space. I'm going to be using a blind walking paradigm, and so for those who don't know, a person would view a target. They would then close their eyes and walk to this target. We record where they walk, and then we guide them back while they're blindfolded. And we just keep doing that for a whole bunch of trials. And that's, in general, a blind walking experiment. This is really, really good, for measuring depth, right? It seems like a complicated task, but it's really not. So imagine waking up in the middle of the night and you need a glass of water. You can navigate that place so well. You just get your glass of water and go right back to bed, half awake. As long as you really know your environment, you encode it at some point, you're really good at navigating there without looking. So we already tested misalignment. I presented on this most recent summer. And we found that in action space, misalignment does not affect depth perception in action space. This was only in front of us. We didn't measure to the side or any eye rotation. But I'm really interested in eye rotation, right? And this is my design. It's super busy. This is all like this because we need to make the most out of our space. So I'm just going to quickly move it and make it a little more readable, right? So we're using 30 degrees and 35 degrees. Those are just the extreme that I wanted to use. And this is an example of what a 30-degree trial would look like. We have our participant standing here, and they have the cone to the right, and they shoot their eyes to the right, look at it, and then they walk to it. Over here is what we expect their vision to be like. So ideally to be those red lines, but in reality it's probably closer to the yellow. And right here is where we would expect their blind walking target to be. Or judgment, not target. And you can see it's a little shifted to the right and a little shifted down. And so that's what we expect to find. But remember, in near space, we expect the pupil sum to be stronger. So we're going to do this again, but in a blind reaching task instead. Same thing, instead of walking, you're reaching. And our target is going to be this circular disc, and it's going to be presented at head height. And so we expect the same thing, but probably a cleaner result out of this because it's in near space. And the expected data would come out more or less like this. Right? This is fake data, not real data. It's shifted over in the direction that the object is placed. There's nothing too fancy going on here. They're just more rolling to whichever direction the object is presented. So, also we need to present in front of the subject too, and I want to talk about that. So again, we're having convergence, and the closer it converges, the more off they'll be. So in near space, we expect to see something like this. All right, so action space, we don't get an effect, but once you cross interpersonal space, you can see this line start forming, and that's the effect of our delta theta happening and coming into effect real time. If we were to rely completely on our convergence here, you would get an underestimation of about like about 60%, which is crazy. Obviously, we probably won't rely completely on convergence, but still, our depth perception is a weighted system, so it might pull it down quite a bit. To wrap up, I want to touch on what's next. I mean, truthfully, I don't want to present a problem and not give a solution. I mean, that's really just nitpicking at that point, and we don't want to do that. Recently, SR Research had the pleasure of seeing this in person. They've been expanding to accurate head-mounted eye trackers, and ideally, we could use that to create a individually based spatial mapping of what this individual has in distortion at real time. And now bear with me, all right? We're gonna do some thinking. That's blown out. But you can imagine transforming this into a surface, okay? And we take this surface and we transform that into a mesh that we then present our 3D space on, thus counteracting any distortion that happens preemptively. And while this isn't a perfect solution, I mean, there's still issues with this. It's software-based, and it can be deployed on any headset. So that's really exciting. Lastly, I'd like to thank anyone who helped me with this, supported me along the way. It really means a lot. It was awesome to be with people. What's up?
Can you imagine any sort of hardware solution where like the lens itself
Yes.
kind of adjusts to your, like to stay kind of in proper alignment with your eye, where it's like kind of doing that? I mean, I know that the latencies and all that are challenging, but.
So this has been actually attempted at one point. So the Meta Half Dome did this, and they mechanically moved the lenses with your eyes. And it was really alarming and scary and jerked your head around because I had to move so fast to keep up with your saccade, right?
Yeah.
And they're like, this sucks.
Yeah.
Right? They then moved on, and they're using a different type of lens. It's a stack of polarizable lenses that you can turn on and off and dynamically shift what the focus is. So that really works with accommodation. There's another one that's like, they haven't done anything with it yet. They have a patent on it, and they've talked about it, and it says like it's not really what this technology is meant for. We don't know how well it's going to work. But there's like a generic lens out there that you run a current through, and it will generically make any sort of, like, it can make any sort of shape. And so it does it
flexible material.
Yeah, but does it with like current? I don't remember too much about it right now, but I can send you at least.
I'm just curious if it's like a hardware that like
Software
software would be faster. Of course.
Yeah, software could be retroactively applied and cheaper. While hardware, it's getting there, but it's really behind closed doors right now, and I don't know if we'll ever get there, especially for the consumer. What's up?
Would you expect pupil swing to be exaggerated with people who wear glasses in headsets, and then as kind of an add-on, depending on your answer, would you recommend people just don't wear glasses in headsets?
Yeah, so the question was, do glasses like a compound pupil swim, basically? And the answer is yeah. So if you have a particularly strong prescription like myself, if I close one eye, I can shift the whole room. And you know, that's what you get that stereotype, everyone's clumsy of glasses. It's really because like the floor is not there, it's shifted, it's completely missing in parts. So I experienced that. Do I recommend? So these glasses are particularly designed for you, laser cut for you, so they're really good. actually. It's the generic side of it that gets really clunky. I'd say, I mean, if you're blind like me, I'd wear them. Like, it's fine. We're not flying planes or anything, right? But if we're wanting to do something super high fidelity, like you want to get all as close as you can get. Oh, you're just hair flipping. What's up?
Really cool talk. If I understood the ending there when you were bringing up the iLink eye tracker and kind of some
Yeah.
of these mapping things, that these would be based on the kind of that delta theta based on the eye movement data, right?
Yeah.
So you actually get spatial mislocation of those fixations
Yes,
and
exactly.
undershooting. Do you have a sense of how reliable those would be, given that the ocular motor system itself has errors even when the mapping is right? So especially when you're making large eye movements of many degrees of visual angle, you often do overshoot or undershoot the target without distortion,
Yeah.
just because the ocular motor system is
It's a guessing system.
Is a guessing system, yeah.
Yeah. So when we overshoot, it's not, or undershoot, I don't expect it to be, upwards to 15 degrees. And that's really what we're looking at, right? And truthfully, like a lot of the eye trackers I'm using have 1 degree of error, and they report that. I'm sure it's way worse, actually. So,
You mean in terms of the calibration?
in terms of calibration,
Yeah.
not the iLink
Yeah.
stuff, but like, yeah.
Yeah.
So, it's really capturing, like, it's, again, more of a satisficing problem.
Yeah.
I don't think this will fix it, but I think we'll get a lot
It'll
closer
improve it,
than we
yeah.
are.
Yeah.
And that's really important for a lot of people who struggle to use VR for any sort of reason.
Yeah. Yeah, I think my question was more around was more of kind of I'm just generally curious if you were able to develop these individual maps based on the kind of fixations being off, how stable those would be. So like assuming
Yeah.
perfect calibration, you still get ocular motor error from mislocated fixations. And so I'd
Yeah.
just be generally curious about how stable those maps are. Do you have to do that remapping often, like within a session? Are there individual differences in that success? Because in our work, older folks are difficult to calibrate in part because they show larger mislocated fixations. Their ocular error is higher.
Yeah, and I think you definitely would have to recalibrate it often. Like it's a one-shot sort of deal. I mean, especially if you ever bump the headset, right? Like it's going to get shifted ever so slightly, and that's going to mean a lot to the calibration. So the answer is yes, right? There's definitely issues with it, but it's still going to get us closer.
Cool.
And yeah, I recognize theirs, and I appreciate you bringing that up. Okay. All good? Do we have time?
I think we do, yeah.
Awesome.
What do you